Hey folks, welcome back to my channel. Today I would like to celebrate a special anniversary in the world of CPUs. The 30th anniversary of the Pentium. Yes, back in 1993, on March 22nd, the Pentium processor was introduced by Intel at the CeBIT in Germany. The Intel Pentium is a 5th generation x86 architecture microprocessor, introduced as the successor to the 486 line. The Pentium was originally to be named 80586 or i586, but the name was changed to Pentium because numbers could not be trademarked. As a fun fact, the word Pentium is a mix of the Greek word penta for 5 and the Latin ending for neutral nouns. Well, I have a variety of Pentium CPUs in my collection, and since it's the Pentium's birthday, I would like to give you some background on those different versions. In order to place the Pentium chronologically, I have plotted the transistor count of all Intel CPUs as a function of time, from the 1970s to the 2020s in a logarithmic fashion. The Pentium, launched in 1993, is hence the second generation of Intel's 32-bit processors following the 486. As already shown with examples from my collection, I am focusing today on the first generation family of Pentium processors, spanning the period between 1993 and 1997. These CPUs were codenamed P5, P54C, P54CS and P55C. The original P5, launched 30 years ago, was equipped with 16 kilobytes of first-level cache. This Pentium was produced using a bipolar CMOS technology at a feature size of 0.8 micron with 3.1 million transistors. The max speed was 66 MHz. It was followed a year later by the P54C, having the same first-level cache, however being produced at 0.6 micron with 3.2 million transistors and a max speed of 120 MHz. The third Pentium version, the P54CS, was introduced in 1995 and it was implemented at up to 200 MHz CPU frequencies. The transistor count increased slightly to 3.3 million, but the main change was a significant shrinkage of the silicon die using 350 nanometer BiCMOS technology. The final member of this first generation Pentium family is the P55C, which was introduced only 18 months later in early 1997. With a doubled first-level cache, a resulting largely increased transistor count to 4.5 million, and a further developed 250 nanometer CMOS process, this Pentium represents the most advanced processor in this comparison. Another main step forward at the time was the introduction of the so-called MMX instructions, which were greatly improving multimedia tasks such as encoding and decoding media and video. This overview displays all desktop CPU package types, ranging from the top gold 273-pin ceramic pin grid array to the 296-pin ceramic staggered pin grid array and the staggered plastic pin grid array for sockets 4, then 5 and later socket 7 compatible motherboards. Next, I would like to dive deeper into the silicon die structure of the 4 Pentium versions and compare them visually. In order to do so, I need to remove the lid of the CPUs at the back via a heat gun, for example, in order to reveal the delicate silicon die structure. I will, for time reasons, only focus on the decapping of this 75 MHz P54C. Okay, let's start. Okay folks, here are the 4 Pentium types from the mid-90s decapped. You see the strong die shrinking effect coming from the early 800 nanometer technology of the P5 to the 600 nanometer P54C to the 350 nanometer P54CS and finally to the Pentium MMX P55C produced at 250 nanometer structure size. In the following overview, the comparison of the Pentium die manufactured at decreasing process nodes is shown using the same scale. While the die of the P5 is almost 300 square millimeters large, the die of the P54C shrinks to half the surface size, and the P54CS even lands below 100 square millimeters. The Pentium MMX is larger again with 141 square millimeters due to its increased transistor count. So what was so special about the Pentium architecture? Actually, the P5 was the first superscalar x86 microarchitecture, which means that at least 2 instructions per clock can be executed. This was made possible by a dual integer pipeline design, which was the first of its kind in such CISC microarchitecture. But there were further features that helped boosting the overall performance, such as the dual integer pipeline design, the separated code cache and data cache being now two-way associative rather than single four-way as with the 486, a further developed floating point unit being up to 15 times faster than the 486, a wider data bus of 64-bit, and last but not least, a branch prediction logic. Anyone remembers the Pentium bug? The so-called floating point division bug, or short FDIV bug, was probably the largest recall in the CPU history, costing Intel almost a full quarter's revenue in the range of $475 million US. It all started by switching the FPU design from the shift and subtract division algorithm, which was implemented in Intel's 486DX FPUs, to the Sweeney, Robertson and Tocher algorithm with the intention to double the result per clock cycle. This algorithm requires a programmable logic array, PLA, to be loaded with values between -2 and +2. When the Pentium PLA was compiled, 5 out of 2048 cells were wrongly downloaded, and the subsequent etching gave cells containing zeros when they should contain +2. In the division calculation example, the FDIV bug is visible for simple but specific division. The Pentium bug can show itself in this example as an arrow starting from the 4th digit onwards. I have compared two Pentium P5 versions, the faulty SX835 with C1 stepping on the left and the SX974 with D1 stepping on the right, where the FDIV bug was eliminated. From distance, the two dies look exactly the same. In addition, there are no clear mask markings for the stepping change from C1 to D1. Also here, no difference is visible. Looking deeper, however, the dies are different at the edges and corners. For instance, additional bond pads are visible, here on the right. So the CPUs are different, but it is difficult to pin it down concretely to the FDIV debugged stepping. My hope was to find the 5 repaired array cells, but finding those 5 out of millions of transistors was probably illusional. Anyway, I will give it a try, focusing on the FPU area of the chips. Okay folks, it's a wrap! The first Pentium family is a unique piece of CPU history, and I hope you enjoyed watching this as much as I making this anniversary video. Thanks for watching and stay tuned for more CPU related videos on my channel. Finally, let's enjoy some more microscopy flybys of the various Pentium chips.